Decision 2 from 2024, let's just do it. So we can see here from this flow network, the circled numbers are what's actually going through the pipes. The uncircled numbers are the maximum amount allowed. Now we can see coming into T here that we've got 11 plus 5 plus 16, which is 32 going in there, which means that coming out of S, we also need 32. So x plus 12 plus 10 must also be 32, which means x must be 10. Likewise for Y, we've got 10 plus 5, 15 going into C right now. That means we need to have these things adding to 15, which makes Y 7. The initial flow is the 32 that we mentioned before. The capacity of C1, now we're looking at the maximum capacity of each arc and adding those together, so it's 13 plus 12. We don't have this 7, because you've got to imagine C1 going down here, and we're looking for arcs that go from the left of C1 into the right of it. So you can almost imagine colouring this entire section. We're looking for arcs that go into the coloured section. BC flows outwards. It goes from the right to the left of the cut, essentially. So we do not have this number, but we do add this one. And this one, so that's going to be 13 plus 12 plus 12 plus 11, which will be 48. By inspection, can we increase this by 4? Well, I don't want to increase this by 3 and then increase this by 1 or anything like that. So let's just increase this by 4. That's fine. So we've got 4 more coming into here. Increase this by 4, that seems to be fine. Increase this by 4 seems to be fine. Now, the only thing coming out of F is this, which we can't increase by 4. However, we could decrease this by 4 because it's going backwards, only to then increase this by 4 to get us to T. Let me explain that why that works. If we're increasing this by 4, we've got 4 too many units going into F. But if we shut down this valve, that decreases the amount going into F by 4, which balances that out. And if we're shutting down this valve, we've got 4 too many units going to E, which means increasing this by 4 balances everything out perfectly. So essentially, if the arc's going the wrong way, instead of increasing it, you decrease it, and it works out fine. So the route is S to C to D to F to E to T, and that'll be that done. Using this, prove this is a maximal. Now, this is all about using the max flow min cut idea. So we need to find a cut in here that adds to make, 32 plus 4 to make 36. It's not that hard to find. It's just this plus this plus this. Not plus this, because this is going the wrong way. Just plus that. So 2 plus 13 plus 5 plus this 6. Ignore the 4, because it's going the wrong way in the cut. That makes 36. Min cut max flow theorem says that means that's the maximum flow. Maximum feasible flow. We've got a flow of 36, therefore it is the maximum. And now a vertex restriction is applied to E such that we can only put 12 things through it. Right now we're putting way more. We're putting 15 through it. So how do we draw that first? Well, what we do is we say E in, line E out, with a line going max 12 there, to show that we can only send 12 through E here, and then just connect all the other lines and label them all as they previously are on here. They're not bothering with the circled ones anymore, so I didn't bother with those either. This is the picture. State the value of max flow. Well, if you're lazy, you could just say that, noticing that 3 less are going through E now than before, just decrease this by 3 for 33. Or you could find this cut, 12 plus 5 plus 16 is also 33, I believe. So therefore, again, by min cut max flow, it must be 33. Question 2 then, it's kind of an interesting question. I think I did this in a really stupid way, I think, to be honest. UN plus 1 and UN. So I made expressions for those. I made this one UN plus 1 by just putting n plus 1 everywhere. And then I put this expression into here and this expression into there. So once again, so I've taken this expression and replaced it with UN plus 1 here. And then I put that new expression into there and replaced this UN with this here as well, with just the A on the outside, left everything else alone. And now I did a bunch of expanding and a bunch of collecting. I wrote 3 into n, or 3 to the power of n plus 1 as 3 to the n times 3 to the 1, which is just 3 lots of it. And then I collected those things together. I factorized out common terms like this, and then I just compared coefficients. So this is an identity because it always needs to be true, which means any coefficient of any similar algebra needs to be the same. So there's no 3 to the power n's over here. So that means this thing here must be 0. And there are bn squareds over here, so this must be equal to b. I've also factorized out an a from that before saying it needs to equal 0. I mean, 10 has to equal c, and 6 plus a has to equal d. So okay, from here we can solve this because a is non-zero, big A, which means this bit must be 0 to make this 0. So then for little a is minus 3, we can put this in here and we can solve for b, and then we can put that a also in here and we can solve for d. And that's how I got those constants. Probably a stupid way of doing it, but whatever. Explain why we need to write a dummy demand point, because the procedure that we're about to do doesn't work if the supply and the demand don't match. Dead giveaway that this box here is blank because this stuff doesn't add to make the same stuff as this stuff. If you look closely, Other exams for which that's not the case just give you the total here, I think. Last I checked, so that's super helpful. So we need a dummy thing here, dummy demand point, to make that balance. Demand currently adds to 87, supply currently adds to 105. So they don't equal each other, so that's fine. So what we do is we add 18 extra demand in to make 87 into 105. So now these two things match, and we could maybe write 105 here. Now, of course, this doesn't really exist. We don't really need to give D anything at all. So it's not going to cost us anything to give them anything, because we're not actually going to give them anything. It's a made-up shop. So we're not actually going to ship anything here, so the costs are all 0. So that's that completed there. And now it says by finding, or it says by doing something, it gets this here. And now we need to start with GD and do another lot of this procedure here, the stepping stone method. So okay, we just put theta in GD because it told us to. Now, do we decrease this one or this one by theta? Well, we can't decrease this one by theta because there's nothing to then, in this column, balance that theta out. So this one decreases by theta, and this one increases by theta. Now this row is balanced. I haven't put that in yet, apparently. I've now decreased this one by theta because obviously that's the only one in this column that can be decreased, which means this one needs to increase. And like I said, this one increases to balance out that theta, which means this one needs to decrease, which also balances out that one, which means this just needs to be a 21. And we're good to go. We now maximize theta. All of these need to be positive or 0. So the max theta can be is 6 to make that one 0. And we end up with this. So the entering cell is GD, and the exiting cell is GB, or BG, I guess. And yeah, now it says do 2 iterations, right? So now what I need to do is I need to draw out the cost matrix. So this is the costs of the routes that I'm actually using. I'm using this route, this route, this route, and so on. This is the costs of those routes. These costs are 0, of course, because that's a made-up demand point. So it doesn't cost us anything to send anything there. And now we do the improvement indices and the shadow costs. So start here at 0, and start here at 0. This one needs to be 23. This plus this needs to equal this. This plus this needs to equal this. This needs to be a 3. This plus this needs to equal 19, so that needs to be a 16. This plus this needs to be 24, so that needs to be a 1. And you keep going. The next one to spot is this one over here. This plus this needs to be 0, so that needs to be a -1. So therefore, that also needs to be a 1. So therefore, that needs to be a 19. And now we take the amounts in the initial cost matrix up here. And for example, for this entry, we do this amount here minus this minus this. So 28 minus 16 minus 0 is 12. 22 minus 19 minus 0 is 3. 0 minus -1 minus 0 is 1. And so on. That exact method just keeps going and going and going. If you see a -1, that means it's not optimal. So you take the most negative, which is that one, and that becomes your new entering cell. So now you go back to this thing over here, you put a theta here, you do the same thing we did over here where we balance out all the thetas. So this is going to have to be a minus theta because this can't be, because this doesn't exist. I just put a 0 here because this one went away. There's nothing to balance with this 19, so this needs to be the minus theta. There's nothing to balance with this 21 either, so that needs to be the minus theta down, sorry, the plus theta down here to make that balance, which makes that a plus theta, sorry, a minus theta to make it balance. And I think now everything just works. Put in a 6 and a 23, and now maximize theta by choosing theta to be 12 to make this one go away. And if theta is 12, all those become that. So the entering cell was FD, the exiting cell is HD, just like I've said there. And yeah, this is all good to go. We now say state the cost of this. Well, it's 21 times 23 plus 1 times 26, because remember this is how much it costs to do any of these things, plus 19 times 19 plus 12 times 0. We should probably be looking at this matrix, to be honest. Plus 6 times 0 plus 23 times 20 and so on. Eventually you end up with this number here. Is this optimal? Well, what you need to do is you need to do one more round of this, but only halfway, so it's okay. Get out the cost matrix for the routes that you're actually using at the moment. Start with 0. This needs to be a 23. This needs to be a 3. This needs to be a 16. Next one I think you can get is this one needs to be a 1. How did I get the... Oh, sorry, that's the -3 because 0, 3 and 3 makes 0, which means this needs to be a +3. That needs to be a 17, and that needs to be a 1. And again, now for this one, do this minus this minus this. For this one, this minus this minus that. This one this one is this minus this minus this, and so on. They're all positive, so this is optimal. So you say all the improvement indices are non-negative, so this is optimal. And that is that question done as well. A shame on question 4 that we don't actually have to do the Hungarian algorithm, because I think it's really nice and easy and gets all our marks, but we don't actually have to do it. All we have to say is how we would set this up to start a Hungarian algorithm. Well, Hungarian minimizes things. It doesn't maximize things. So we have to look for the biggest number in this table, which is 77, and we need to do 77 minus every entry in this table. Because what that essentially does is it turns all the numbers that were big into numbers that are smallest, and all the numbers that were smallest into numbers that were biggest. And so then by minimizing that new table, you end up maximizing the old problem. Also, with these dashes, you just need to make up numbers to go in there. We'll just replace those with the numbers 1,000, like this. So this is every entry having 77 take away. So 77 minus 65 is 12, 77 minus 72 is 5, and so on. Replace the blank ones with 1,000, because this essentially means Hungarian will never want to use these two boxes because they're so much bigger than everything else, which means that since it won't use them, it doesn't matter that it can't use them, because it just won't. And this is all good to go. You now just need to minimize that, and that'll be that done. They asked this question identically in a paper a couple of years ago, so probably something that's just worth memorizing what to write down. You say worker I is A, B, C, or D, and job J is P, Q, R, S, or task, I probably should have written, but whatever. And now you define X, Y, J to be 1 if they're doing the job, and 0 if not. So essentially you're trying to build a table that just goes 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, or so on. And the 1's just denotes that worker C is doing that job that there's a 1 there for, and 0 just denotes they're not doing it. Because you want one worker to do each of the 4 jobs, and you don't want any overlap between jobs, and you don't want 2 workers doing any particular job. So you just want 1 if they're doing job and 0 if not. Now you need to minimize, of course, 12 times if whatever the entry is. So if worker A is doing P, then it will be 12 times 1 plus 5 times 0 plus 8 times 0 plus 2 times 0, because A won't be doing any of the other jobs, plus whatever's here, and so on. And you want to minimize that amount. That's the entire idea here, is minimizing where the 1s go, such that that calculation is as low as possible. But okay, the one extra constraint, I've said it out loud a few times now, is that you can only have 1, 1 in each row and each column. And the way that we write that is this, xaj. So the x that refers to the A row, for whatever j there is, the sum of those things needs to be 1. In other words, if they can only be 1s and 0s, and there can only be 1, 0, because if you add them all up, sorry, there can only be 1, 1, because if you add them all up, you need 1 plus 0 plus 0 plus 0, or 0 plus 1 plus 0 plus 0. You can't have more than 1, 1, because then worker A is doing more than one job, and therefore the sum would be 2, and you can't fill anything in with anything other than 0, 1. So this suffices to just say that A is doing one job and one job only. And likewise for B, and for C, and for D, and then likewise for the jobs themselves. Each job can only be done by one person, and must be done by one person. So the sum must be 1, because it must just be a bunch of zeros adding in with 1 exactly. And that is how we formulate it. And that, I think, is all we need to write. Question 5 then is the decision tree question. So we start with a rectangle, then we do circles. The decision goes to the circles, and then of course the probability goes to the triangles at the end. So let's start up here first. So the decision is plane, train, or coach. Plane, there are 4 things that can happen. It can be on time, it can be 1 hour late, 2 hour late, or 24 hour late. So there are 4 things that can happen. The probability for each is here. You need to work out the probability that it's on time is just 1 minus these things, which is 0.83. And now we just need to work out the cost of each thing. So if it's on time, well, the plane in general costs 200, and then it costs 3 hours, and he's timetabling his time to be £50 per hour. So that's 3 times 50. So it's 200 for the ticket, and then 3 times 50 for the amount of time he flies. That's 350, and then that's that for on time. For late, it's going to be 200 for the cost of the plane ticket, plus 4 hours, because if it's 1 hour late, then it's 4 hours in total. So it's 4 times 50, which is a cost of 400, and so on for 2 hours late, and for 24 hours late, that will mean it will take 27 hours in total. So the cost will be this, which is this. Now to work out this circle, we just do this times this, plus this times this, plus this times this, plus that times that. And you calculate that equals that number there. And now do not do this in your exam, but I am going to get rid of that because I need some space for the train. I couldn't have fit it. Or I probably could have fit it in. Anyway, I can't fit it in the coach. So we just say that we're going to keep that there. You've got an entire A4 page to work on the exam, but I'm going to delete it for now. I'm going to say these are my triangles here. For on time is 1 minus this, which is 0.9. You do need to write the probabilities in here, by the way. You do need to write them in. Anyway, and now we can work out the amount. So train is 130, takes 5 hours. That would be 5 times 50 plus 130, which is this. And then this will be 6 hours times 50 plus 130, and this will be 7 hours times 150 plus 130. And then again, it's just this times this plus this times this plus this times this, which is that. And now, again, get rid of that because of that space. For coach, there are 4 options: on time, 1 hour late, 2 hour late, or 3 hour late. I should have mentioned before, apparently you don't need to draw options that have probability 0, although maybe it's safest if you have space to do that anyway and just write it, because it's not going to make a difference to the calculation in the end, of course, because 0 times something will be 0, so it won't add into this. But yeah, the mock scheme says you didn't need to, so I didn't bother. I'm crammed enough for space as it is, so I kept it short. Anyway, these are the 4 options that can actually happen. So we have here, it's going to be 70 plus 6 times 50, and next one will be 70 plus 7 times 50, and so on. And 9 times 50 gives you this. Again, one more time, this times this, plus this times this, plus this times this, and so on, gives you this amount here. The lowest of these options is the train, so he should choose the train. Now, I've been quite lazy on question C because I couldn't be bothered to redo all of that. So I'm just going to do it for the coach and explain what to do. When you have a cube root utility function, all that means is you cube root all of the costs. So we're going to cube root this, cube root that, cube root that, cube root that, which of course means in the calculation, we're going to do this cube root times this, plus the cube root times that, plus the cube root and so on, which apparently equals this, which is this number here, and you just do that for the others. So going all the way back to the train, again, just cube root those 3, put the cube roots in here, work out the new amount, and again, you just look for the lowest, and apparently the lowest is for the plane, and so that will be the answer to C. Question 6 then, the dynamic programming question. So let's call this stage 1, stage 2, stage 3, stage 4, stage 5. We're essentially just minimizing, right? Because if we want to start the latest time possible, we just want to minimize the journey time to get finished by 9 p.m. So stage 1 can either be H, I, or J, and of course we need to go to T. This column feels a bit pointless to write just the same thing you wrote here, but we're going to have to do it anyway. And now, of course, the value is just 2, 3, or 4. And star them all because those are the best choices to get to T from each of the starting points. Stage 2 is F or G, so we'll start with F. F can go to R, H, I, or J. Again, this column feels kind of pointless, but anyway. Now, F to H is 5, and then the best choice from H is worth 2, so that's going to be 5 plus 2 is 7. F to I is 4, best choice from I is worth 3, so that's 4 plus 3 is 7 as well. F to J is 6. Best choice from J is 4, 6 plus 4 is 10. So we don't want to be doing that one, but either of these two is fine, so star them both. And from G, we can either go to H or I, which is 5 plus 2, or it's 3 plus 3. And the best choice is this one here. So basically, if we ever find ourselves at G, we're going to choose the I option, which gives us total distance of 6, and that's why we're starring them, is to find it super easily. Stage 3 can either be at C, D, or E. We'll start with C, which can go to F or G, and that's going to be 3 plus the F journey, which is 7, or it's going to be 4 plus the G journey, which is 6. Both of those are the same, so we start both. For D, we can either go to F or G, and you can feel me bored already because it's basically the same thing every time. It's 3 plus the best F choice, which is 7, or it's 1 plus the best G choice, which is 3. We choose the best one, which is this one here, and then we go to E. Only choice is G here, so that's 2 plus G's best, which is 6. Star it, and then from 2, option 2 or stage 2, it's just A or B. We'll start with A, and we just do the same thing again. I'm bored, so I'm just going to scroll through. You can check my numbers if you want. There are 3 choices for B, so there's a bit more to do, but it's honestly not that bad. And then from the very start, we can either only go from S to A or S to B. S to A is 3, the best choice from A was 13, so that's going to be 3 plus 13. S to B is 12, the best choice from, S to B is 2, the best choice from B was 12, so 2 plus 12 is 14. And we star that, and the best choice is to go, well, it takes 14 hours is the best journey. 9 p.m. take away 14 is 7 a.m., so that would be our starting point. And we should go S to B, to E, look for the stars, to G, to I, and from I to T, of course, and that will be our route. The game theory question then, there's no stable solution if there's no saddle point, which means the row maxi-min equals the column minimax. These are just if or only if conditions, so you can just look for them. So the row maxi-min, So we're looking for the maximum of the minimums of the row. So the row minimum here is -3, here is -2, here is -1. The maximum of those is -1. For the columns, the exact opposite, looking for the maximums and choosing the minimum. So the maximum is 4, maximum 3, maximum 6. The smallest one of those is 3. Those two things are not equal, so therefore there's no stable solution. Player A plays with probability P1 for R, P2 for S, P3 for T. And want to do some simplex algorithm, apparently. So, okay, well, to do simplex, we need to add 3 to all of these because simplex doesn't work if any of these are negative. They're allowed to be 0, but that's fine. We just add 3 to every one, so this will be the table we're actually going to work with. If player B chooses X, then our winnings in this game, where we've added 3 in, our winnings will be 6 times the probability of playing R, which is P1, plus 7 times P2, plus 2 times P3. And our winnings will be less than or equal to that, because of course our winnings might be more for a different option. So whichever one we end up choosing, but it will be less than or equal to that, because the options might not be the best option to choose, essentially. Anyway, the next one is the same, so just read down these numbers, use them as your coefficients in case pair B chooses Y, and then likewise the next one as well. We also need P1 plus P2 plus P3 to equal 1, although actually, for simplex, we always just say that it's less than or equal to 1, because that way we can add in a slack variable, which actually allows us to do simplex, I guess. And of course, P equals V means that we will rearrange. We need to rearrange all these as well, though. So let's move all of these to the same side as we do in D1 simplex and add in S1 to make it equal 0, because of course we'll be less than or equal to 0 if we add all these over. So add in our slack to be equal to 0. Likewise with the one underneath, and likewise with the one underneath, just add in S2 and S3, and just add in S4 here to make it equal 0 there. And that gives me an S1, S2, S3, S4 to put in these rows here, and likewise down here as well, which is perfect. P equals V also means P minus V equals 0, and that's going to be this row as well. So perfect. Put all those in, put all those in. Now just read the coefficients. 1, -6, -7, -2, 1, 0, 0, 0, 0. Perfect. All good. Next one. This is from the S2 because it's got the S2 in it. Write those in, just the coefficients. Pretty straightforward. More coefficients for this one, and finally the coefficients for that one as well. And that will be that done there. After several iterations, which thank God we didn't have to do, they end up with this table here. State the best strategy for A. Well, we can read here that we've got our basic variables here. P1 apparently needs to equal 3/8. So P1 is 3/8. P2 we can see is 17 over 80. So we play R with, remember R was, P1 was denoting the probability of playing R. So play R with probability 3/8. Play P2, play S with probability 17 over 80. And of course we can do 1 minus these two to get P3, which is the probability of playing T, would be that there. So that's their strategy. The value of the game is just this number here. So from B's point of view, this is the value of the game from A's point of view. Of course, whatever A wins, B loses. So the value of the game for player B is minus this, except remember, all the way back, we added 3 to everything to make it all positive. So let's take away 3 from that first, so that we have the value of the game originally. But of course, remember, like I said, that's a negative value because B is losing money in this scenario. But that's the value for him. Player B intends to make a random choice. So what we'll do is we'll call those choices Q1, Q2, and Q3, because that's what we always do in these questions. And what we'll say is the value is -25 over 16. So except what I've said is I'm just pretending that I'm working with the fake game that's adding 3, because I couldn't be bothered to redo it, because that way I can just read the coefficients that I've got up here. So we read across this time, because assuming player A plays option R, it's just the same as we were looking before. 6 times Q1 plus 5 times Q2 plus 0 times Q3 equals the value of the game, which is this. Now, again, to B, the value is minus this, but to B, all of these values should be minus, because anything A wins, B loses. But of course, if you make this minus and these minuses, then you may as well just be making them more positive. So let's just make them more positive. Next row, same kind of thing. And the row after that, the same kind of thing. Why have I got a 3 there? That's super annoying. That should be a 4, but I cannot be bothered to fix this or to re-record it. I'm just going to say out loud, that number there should be a 4. If you type this into a calculator correctly to solve a 3D simultaneous equation, you'll end up with these 3 numbers here. And so, and be careful here, you actually need to write in context that player B should play X with this probability here, should play y with this property here and z with this property here. Not enough to just write down the properties like this. You actually needed to state them. A sneaky edit anyway, you can see that I've changed this to a 4, which is what it should be. Also bear in mind, just in case you ever need it, you do have a fourth equation you can use here, which is q1 plus q2 plus q3 must equal 1. So you could also use that equation. You don't need it here because 3 variables, 3 unknowns. 3 equations, 3 unknowns, 3 variables. But in case you didn't have one of these for whatever reason, just maybe you knew that player A wasn't playing one of these options at all, then you'd still have q1 plus q2 plus q3 equals 1 as an option you could use for your calculator to solve it. Anyway, question number 8 then is a recurrence relation question, which is great because they're obviously super easy. Just move the 3 over here. Just focus on this step here and make a quadratic 2m squared plus 5n minus 3 equals 0. Solve it in a calculator, I guess, or by factorizing, it's up to you. And then put the solution as a, this one to the power n, plus b, this one to the power n. That's the first bit. Then we focus over here. We say un equals maybe lambda n plus mu or kn plus l, because I couldn't be bothered to type those Greek letters into PowerPoint. Un plus 1 is just this. Just replace the n with n plus 1. Un plus 2 is that. Shove those 3 results into here. And now, like we did earlier in the paper, just compare coefficients. You might want to expand out and collect everything first, like I've done here. But now, the only n's over here are 4k of them, and there are 8 over here. So 4k equals 8, which means k equals 2. And then once you've got k as 2, these constants over here must all equal 2. So you get 18 plus 4l equals 2, which means l is minus 4. And put those results into there, combine it with the original result you found over here, and you end up with this equation there, and that'll be those 5 marks. The last part of this question is actually kind of interesting. We have u0 equals 1, so perfect. Put n equals 0 in and replace this with a 1. All of this basically goes away. You get a plus b minus 4. Add 4 to both sides, you get this. Likewise, put 1 in here and put in a k, and you get this. You can simplify this a bit, and probably the best thing you can do is write it like this if you double everything and move some stuff over. Now, okay, well, we want to solve this for a and b, but we're only going to do it in terms of k. But that's okay. Just do this minus this. Actually, no. Maybe this minus this to get a positive b. Sure. B minus 6b is 7b. Divide by 7, and then maybe put this in here. I think I've times all this by 7, just so I can put 1 minus k in instead. And then write a as this after doing a bit of rearranging. So, okay, replace a and b with those 2 figures there. And now it says all terms are positive, k is a positive constant, determine the value of k. A little bit of intelligence needed here. If all of the terms in the sequence are positive, this term is the one to think about really carefully. If n becomes really, really big, and specifically really, really big and odd, then minus 3 to a really big odd integer is a massive negative number. In fact, it's way bigger than anything the 2n will provide, and way, way bigger, because of course half the n tends to 0 as n gets really big, than anything this will provide. So if n is a very, very large odd integer, this term is going to make the entire thing negative. It just will, because it will massively outdo this number here. But that's a contradiction to what it says here, which is that all the terms are positive. So how do we fix that? Well, we make the coefficient of this thing 0, because that's the only way to get rid of it, to ensure that it never messes everything up and makes the whole thing negative. So we set this to be 0, which of course means k is a half. And that'll be our answer. Thanks for watching, and I'll see you next time.